Lesson 8-8, Systems of Equations, and in this lesson you learn to solve systems of linear equations by graphing. And in this lesson it is important because systems of equations can be used to determine the cost of two telephone calling plans. And let's take a look at that activity. Between 1984 and 1994, the number of cellular phone users doubled more than 7 times. So in a questionnaire concerning phone service, potential customers were asked whether they would prefer to pay $10 a month and 10 cents for each local call, or $5 a month and 20 cents for each local call. Is there a certain number of calls where the two payment plans result in the same total cost? Okay, so we look at the two plans. To solve this problem, let n represent the number of local calls made in a month, and let c represent the monthly cost. You can write two equations to present the situation above. Plan 1 would be C, the total cost would be $10 a month and 10 cents per call. And then the other one would be, the cost would be $5 a month plus 2 cents per call. Okay? And then we can basically use a table of values, okay, to be able to find where they would be equal to each other. Okay, we're at the point where both calls, okay, where the two payment plans result in the same total cost, when their C's would be the same. So if we use table of values, this is what's going to come out. Basically, we represent C equals 10 plus 0.1n, and we represent n as 0, okay, all the way down to 90. Okay, that's our domain. Our y value, which is C, will be the following values given here, 10 all the way down to 19. Now if you notice at this point, at 50 and 15, okay, their costs would be the same. So in plan 1, okay, if 50 calls were made, the cost would be $15. Same thing with plan 2. If 50 calls were made, it would be, the cost would be $15. Okay, so we located the row where the outputs are the same. What are the identical outputs mean, and why it happened? Basically, it's saying that the x will be equal to 50. That will be the number of calls. The cost is the same for both plans when 50 calls are made. Okay, so we didn't have to use a graphing calculator for this. I did this for you in an Excel worksheet. Okay, now the two equations that we just talked about, C equals 10 plus 0.1 n, C equals 5 plus 0.2 n, together are called system of equations. The solution to this system is the ordered pair that is a solution for both equations. So in this case, the solution is 50 and 15. So refer to the outputs in the situation above. What is the solution to the system of equations? We already talked about that. It would be right here, okay, would be 50 and 15, right? So another method of solving system of equations, well, let's write this down, okay, right there, because that's where they are equal. Let's go back here, okay, and let me show you that again, since in case you have a bad memory. Right there, 50 and 15, okay, where the two costs will remain the same. And let's go back here. Okay, so another method for solving a system of equations is to graph the equations on the same coordinate plane. The coordinates of the point where the graphs intersect is the solution for the system of equations. So let's graph, okay, y equals 2x and y equals negative x plus 3. Okay, we need to solve the system of equations by graphing. So we have equation 1 and y equals 2x, and equation 2 y equals negative x plus 3. Let's graph y equals 2x, y equals negative x plus 3 on the same coordinate plane. Okay, and let's first graph y equals 2x. Remember our methods for graphing. Okay, you can use the table method, you can use the intercept method, or you can use the slope-intercept method for graphing an equation. Okay, let's use the slope-intercept method in the last lesson. So let's say, to be able to graph this, let's first graph y equals 2x. Okay, and let's use the method y equals mx plus b. Okay, where b is your y-intercept. Okay, remember that. This was from the last lesson. And m is your slope. Okay, so if we follow this procedure, our slope would be 2. And since you don't have a b, our b is equal to 0, because you can add 0 there, and that would be your b. So remember how we graph this. First thing we do is we need to graph the y-intercept first, which is 0, right here. Okay, then after graphing 0, we use the slope to graph the other point, and since the slope is 2, the slope is the same as 2 over 1. If the slope is 2, rise over run, that means our rise is 2, our run is 1, and since they're both positive, okay, we rise 2 steps up, okay, and 1 unit to the right. So 2 units up and 1 unit to the right. Graph that other point, okay, and that's a graph of y equals 2x right there. Okay, let's graph y equals negative x plus 3, following the same procedure. Okay, and y equals negative x plus 3, our slope will be equal to negative 1, or negative 1 over positive 1. You can also use 1 over negative 1. It doesn't really matter. It's the same. And our y-intercept for this one would be positive 3 right there. Okay, so we'll use another color, use green. So let's graph our y-intercept, which is 3. 1, 2, 3 right here. Okay, and our slope is negative 1 over 1. That means our rise is negative 1. Our run is positive 1. That means when your rise is negative 1, you go down 1 unit. Okay, and then you go to the right 1 unit. So it's going to be the same point right there. Okay, and then we connect those 2 points. Connect those 2 points. That's our line. So if you notice, okay, after graphing both of them, okay, the line intersect at point 1, 2. Therefore, the solution to the system of equations is 1, 2. Okay, and to check if our answer is correct or not, we simply substitute 1, 2 to both equations. And if we substitute it to y equals 2x, where x is 1, y is 2, you end up with a true statement. And if we substitute it to y equals negative x plus 3, you still end up with a true statement. So the solution to this equation by graphing is 1, 2. Okay? Let's take a look at example number 2. Example number 2. Solving systems of equations can also be used to solve problems. And let's refer to the application of the beginning of the lesson for this one. Okay, solve the system of equations for 10, c equals 10 plus 0.1n, and c equals 5 plus 0.2n by graphing. Okay, and we will use GeoGebra and Excel to graph the system of equations. Okay, so first things first. Okay, let's use our ordered pairs right here, and let me open up that Excel page right here. I think it's up here. I'm mistaken. Yes, it is. Here it is. Okay, so this is the right there. Those are the units that we used, okay, for our first example, and we are simply going to get these. And we're going to open up GeoGebra, okay, and we're going to plot this. Grid, and then we want to find spreadsheets. Which is, I think, here, right there. I'm going to paste those values right there. Let me do that again. Copy. Go back to Gebra. Paste. There you go. And then we're going to ask that to be graphed. There you go. And we're going to get the other one. Right here, these values. I'm going to copy that baby. Go back to GeoGebra. Paste that. Let's maximize this now. Okay, and let's graph this table of values. Right there. Okay, and then if you look closely, okay, back here now, there it is, right there. Okay, let me close my spreadsheet. Okay. Take that out. Look at this closely. Let me use this. There you go. Okay. The point where they intersect right there is 50 and 15. So this is line 1 and line 2. Okay, the two costs. So if you notice, it intersects at 50 and 15, which is, let me write that down. That point right there. Cancel. Let me write that again. That point will be, oh my goodness gracious. Well, you get the point. Okay, that'll be 50 and 15. Okay, well, it's gone now. So that is how you graph that particular system of equations if you are not going to use a table of values. Okay, so you notice that the graphs intersect at the point 50 and 15, and if you want to check if our answer makes sense or not, you simply use the two equations, c equals 10 plus 0.1n, and substitute the values 50 and 15. It will come up with a true statement. Get the other equation, c equals 5 plus 0.2n, end up with the same, okay, true statement for that one as well. Okay, so the solution is 50 and 15. This means that the two payment plans result in the same total cost, $15, when 50 calls are made. And we talked about that as well. Okay, let's take a look at the last example. Before we do that, as you can see in the examples above, when the graphs of two linear equations intersect in exactly one point, the system has exactly one ordered pair as its solution. It is also possible for two graphs to be parallel lines or to be on the same line. Again, there are two possibilities here, and take note of that. Okay, two graphs to be parallel lines, or two graphs can be the same line. When the graphs are parallel, the system of equations does not have a solutions. Do you remember why? Because when the graphs are parallel, they have the same slope. Okay, that means if they have the same slope, okay, they will never intersect. Okay, that means they are parallel lines, and therefore you won't have an intersection of those two lines. Okay, so if you want to solve the system of equations by graphing y equals x plus 3 and y equals x plus 4, okay, and if we use again the slope-intercept form for this one, the first one, let's tackle this one first. Let's do the green one. Y-intercept is 3 right here. Okay, and the slope is 1. Okay, so that means 1 rise over run, positive 1 over positive 1 unit up, and then 1 unit to the right. That's your other point, and we plotted y equals x plus 3. That was easy enough. Well, doesn't want to be plotted, so I'll plot it myself. Okay, and we'll use green. So we have plot those 2 points. Where is my point? Okay, let's do that again. Okay, that'll be our graph right there. And if I extend this further, there you go. That's our graph for y equals x plus 3. And let's graph y equals x plus 4. And our y-intercept is 4, so we start at point 4 right here. Let's make that blue. And since our slope is the same, so that's 1 unit up, 1 unit to the right. Okay, and I plot it this time with a color blue. Okay, there you go. Thin line, and I connect those 2 points. Oopsie, doesn't look like a straight line to me. This one will. Okay. So I connect those 2 points, and if you notice, they're parallel to each other. And they will never intersect. And that's the reason why the solution of 2 parallel lines, okay, will be no solution, because they will never intersect. Okay? 2 parallel lines will have the same slope, but they have different y-intercepts. And take note of this one. They will have the same slope, but different y-intercepts. Okay? And in letter B, y equals negative 2x plus 3 and y equals 3x minus 6x plus 9. And if we graph these, okay, this is what we're going to end up with. Okay? So each equation has the same graph. Any ordered pair in the graph will satisfy both equations. Therefore, there are infinitely many solutions to this graph of equations, which simply means this. Okay? The graphs have the same slopes. Okay? And they have the same y-intercepts. Okay? If you notice, y equals... Oh, that's a good one. Let me use the pen this time. Okay? Y equals negative 2x plus 3, and let's take 3y equals negative 6x plus 9. If you notice, in solving an equation, whatever you do to one side, you need to do to the other side. So if I divide this by 3, and if I divide this by 3, I end up with the same equation, y equals negative 2x plus 3. Same equation, same line, and that's the reason why you only have one line. And since they are coincident, that means they lie on top of each other. Okay, they have an infinitely many solutions. Okay, and I think that's about it for graphing systems of equations. Okay, and our secret word is playoff. Secret word for this particular lesson will be playoff. Thank you for watching.